Hi, Victoria. How are you?
Hello, Katarina. I'm well, thank you. How are you?
Great. I'm so happy you're here.
Thank you. What a great welcome. I'm so happy I can be here. And here's our guest.
Oh, hi. How are you? Thank you for coming.
Hi, thank you.
Yeah, it's really nice of you to take the time to do this. So, thank you.
Thank you for your invitation. Yeah, my pleasure to share our work.
And how has your week been? Everything good? Did you have a
Yes,
good week?
except the cold weather here
Oh,
in
yeah.
Chicago.
How cold is it right now?
So today is around -9 degrees Celsius.
Yes. Okay, Celsius. Good. I
Yeah.
I I do like I refer to temperature as Celsius too. Yeah, that's really cold. That is really cold. Here in New York, it hasn't been a real winter, I feel like. It hasn't been too cold.
Hasn't been. Oh, that's good.
No.
Maybe
And no
because of the
snow.
global warming.
Yeah, it's a second winter that it's not really snowing and not that cold. It's a few days very cold, like a couple of days, but then it gets
Yeah.
back to.
I have the same feeling here this year, especially this year, warmer winter.
Yeah, it's a big difference. It used to snow a lot when I was first here for my PhD in New York. Um, we had like huge snowstorms and it was freezing. Yeah,
Yeah. So that's why we need to solve the global warming as soon as possible.
exactly. I think that's the biggest concern we should have. I think
Yeah.
everything else is just distraction from the real problem. Yeah, I agree. I don't know. Um, I should have gone into that type of research, maybe.
Yes, everybody develop their effort on this issue. I think this problem can eventually be solved if everybody.
Yeah, do you think AI will help us more? Like, do you think that's a
I think so. And right now, the Chat GPT has proven to be very powerful, and uh, and indeed it is.
Yeah, that's my hope that yeah, that maybe technology will help us and come up with new ideas that we haven't thought of before. Um yeah, let's hope that it works because yeah, it would be independent from if governments are willing to pay a lot of people to think about the issues because it's relatively cheap to do it.
Don't
Yeah,
don't
go
you
ahead.
think a lot of the issue though is what people are willing to agree to? That we have answers already, and that the issue is shifting lifestyle and living more compatibly with the earth?
Yeah, I'm not sure if that alone nowadays could still solve it because we need to, for example, have agriculture in a scaled version because we have so much population to feed. So I think, yeah, we probably need to we need to scale down. Like in some countries, I don't think it would be fair for every country because the US and European countries have been historically being the major contributor to this problem. So it wouldn't be fair to tell now countries that just started to develop, yeah, you can't.
No, not at all. It would be, I mean, seriously leaning heavily on countries that were responsible for things like that, like exactly like the United States, moving into other countries and then establishing the same practices,
Yeah,
if
but
that kind of thing.
researchers have
Yeah.
shown that that wouldn't be enough nowadays. Like it's already too late for just changing our habits. We need that and we need to like extract CO2 from the environment and so on. So we would need both.
Right, all of it.
Yeah, we need everything.
Mm-hmm.
But you're right. It's very difficult though with the economic model. I don't know to, you know how it is with having constant growth that we need.
Yeah, that's a huge issue. It's and also
But
that
without it,
mindset.
yeah, but also without it, we cannot afford all those programs and Medicare and healthcare for people that don't have money and support for for science, and all of this is based on that we have a constant growth to be able to afford this. So it's like a catch 22, I think. Is that what you say in
That's the
English?
number.
Yeah, it's very hard. I don't know. That's why I'm saying I hope AI can come up with solutions because it's very complicated, and I don't think none of a singular person has enough knowledge about all the issues involved to come up with a big scale solution. I don't know. But I don't know, maybe not.
It just needs to come up with a solution for greed so that the decisions that we make are made with a social and environmental conscience. You know, especially decisions that involve working at scale, and then um, and then socialism. But we had a really good snow here. We had a really great snow on Tuesday. Just speaking of cold weather, because it's been really cold here too. You know, like it's like -5 in the mornings, Celsius. We just kind of get a pretty snow that doesn't really stick for very long, so it doesn't have a chance to get dirty. It just has a chance to make everything beautiful.
Oh, that's nice. Yeah, that's the prettiest snow. It's right in the beginning. So that's
Yes,
one.
it's nice. And we had a very big snow yesterday, but today most of them uh, were melted because of the sunshine.
Darn that sun. Do you participate in any winter sports, Lon? I
Sorry.
was wondering if you participate in any winter sports involving snow,
Oh
so you can take advantage of that.
no, I play basketball inside, so
That's a winter sport, because otherwise you'd be outside. Okay, cool. Good for you.
I hope I can try skating in the future.
Oh,
It's
right. Are you in the city? Are you in New York City? I'm sorry.
I'm in Amsterdam, a small city near
Oh, in
Chicago.
Chicago. Okay, great. They must have outdoor. I was asking, I thought you were in the city because, but Evanston must have as well outdoor skating rinks. I mean,
Hmm.
I know you could probably just skate on the river, but it's such a beautiful thing to do. There's nothing to hold on to like in an indoor rink. Well, unless you find an outdoor rink. It's just a beautiful thing. Even if you're just learning, I encourage you to try to find an outdoor rink because it is beautiful and invigorating, and it's
Yeah,
nothing like
yeah.
skating indoors. It's special.
I don't know whether it is easy or not. Maybe it's very difficult for me.
But when you fall, you slide.
But
Oh, sorry, Katarina.
yeah, I wanted to say it's I feel like it's less harmful than inline skating like on the pavement because there it really hurts if you fall on the pavement. But yeah, it's really nice. I also like skiing. I don't know if you can try out in a small slope, or if you don't like going down the hill, because some of my family doesn't like the feeling of going down the hill. The skiing where you just walk basically. What's the name? Cross
Well, cross
country?
country skiing, but
Yeah.
you can do a lot on that isn't walking. But what I would recommend is just snowshoeing. Just get yourself some snowshoes
Oh yeah.
and then put them on, and then
Snowshoe.
you're good to go. You can go up and down. You're like a tractor. That's my favorite thing.
Yeah, I
Yeah.
agree. Oh, we have already 8 p.m. so we can start. This was a nice chat. Thank you.
Thank
And
you.
welcome everyone to Science Society. And I know people will still keep coming in, but let's start with introductions so the audience gets to know you a little bit, and we'll go from there. So welcome everyone, and of course a special welcome to you, Long. And um, Long, he was born in Jiangxi province in China, and he did his bachelor degree in bioinformatics at the Huansong University of Science and Technology. And then he did his PhD degree at the Fudan University in inorganic chemistry in the lab of Professor Guo Qingying in 2017. And after that, he moved to Northwestern University as a postdoctoral fellow in Professor Sir Fraser Stoddart, where he's working on the rotational design of catenanes and rhotaxanes using radical interactions. And this is I posted the paper that we're discussing for everyone in the chat and also the website of Northwestern University. And on top is the slide presentation. But before we go into the slide presentation, Victoria would like to ask you a few questions, if that's okay. Thank you.
Thank you for your kind introduction. Yeah, it's my pleasure to be here to talk to you guys about our recent research. So,
Well, thank you again for your generosity, Long. We're so excited to have you here in Science Society, and we look forward to learning about your research. And we'd also like to hear a bit about you to help deepen our understanding of your focus and your process, maybe. So, my question is, if you can think about where in your lifetime, and this can include in your childhood or anywhere along your life, when you felt drawn toward an interest in science, and then maybe where your passion came from.
oh, uh, about the question. So I think it might be when I was around 10 years old. So my mother is a high school teacher in sport, not in science. So, but one day I think he may bring some essay from school from the school lab and for me to play with when I drop the acid on the surface of some rocks, some bubbles were generated. So they, I think from that little experiment, I found my love in chemistry, and that's why after I graduate from HUST, so I changed my major from bioinformatics and back to chemistry. So I think I love chemistry better than bioinformatics because I'm not good at coding things. So that's it.
Yeah, thank you. And it is so interesting to hear when this happens in people's lives. It's often in childhood, and maybe there's a parent or a relative who also has an interest or even a career and shares something. And so to hear what the spark was for you, um, It's a great introduction to hearing more about your work. So can you then take us along your path from when you did decide to major then in chemistry? And I have to agree with you. It
Mhm.
sounds way more fun. It is. To up to today, to the work that you're about to present. So maybe some major points along that pathway that you can share with us, please.
So you mean some story behind the research, or
Are you asking me to clarify my question?
yes,
Yes,
please.
okay. Yeah, thank you very much. So to clarify my question, you had mentioned then that you changed your major back to chemistry.
Yes.
And so there you are in working on your education. And here you are today about to present this work about electric molecular motor. Maybe you can share with us some of the key moments in that journey from there to here that helped shape your work or your even the transitioned your thought to what you're doing today. Maybe some things that influenced you or challenging moments that shifted your way of thinking or that helped you.
Okay. So I think it's mostly because of my PhD background. Uh, as the introduction by Katerina, I did my PhD in Fudan University, but the major is inorganic. Actually, I'm working on some project related to coordination-driven self-assembly by some organometallic complexes. So the major thing is still in the field of supermolecular chemistry. So and I'm very interested in supermolecular chemistry, and especially for the unique mechanical bond, which I will introduce in my talk. And it's a kind of we can say it's a kind of new chemical bond. And so and then after I get my PhD, and then I decide to find a postdoc. And I think mechanical bond is very, very interesting. And then I send Professor Stoddart an email to see if I have the opportunity to do research in his lab. But at the beginning, maybe he received too many emails. I didn't have the feedback from him. But at that time, it's in March 2017. He has a chance. I have a chance to meet him in person because he went to Fudan University to get a award. So because and mostly because he became very famous in 2016, and he is one of the Nobel laureate in chemistry this year, at that year. So, and after I met him in person, and I gave him my CV, and then after several days, he said yes. He said yes, and I'm so happy that I can have this opportunity to move to Northwestern University here in United States and to do the research about the mechanically interlocked molecules, and finally, and we made this electrical molecular motor based on 3 catenane.
Thank you. That's actually an exciting story. It had some twists and turns, you know, like a nervous moment. Maybe you wouldn't get what you wanted, but you did. I also I want to thank you very much for that extra info. I want to welcome Dr. Shaw, who's here to join us. We're so happy to see you, Dr. Shaw, always. And Jeremy in the audience mentions in the room chat that he loves snowboarding. So that was one winter sport that we neglected to mention.
Yeah.
So maybe long you'll take up snowboarding.
Yeah.
Um, and so at this point, the mic will be yours. You're welcome to dive into your discussion. Katarina has shared your Google Doc so people can follow along. And then we are here, Katarina, Dr. Shah, and I, to help with if anybody puts questions for you in the room chat, or if you have something else you wanted us to share there, and also to field questions if people would like to come up from the audience. So unless you have any other questions for us at this point, the mic is yours, and we're so grateful and excited to hear what you have to share.
Okay, great. Thank you very much, and thank you all of you to join Clubhouse to hear my story. So I'm glad to share with you. So let's see the slide from the link, and as you can see, the first slide is uh, a structure of the electrical mercury motor. So my name is Long Zhang, and from Northwestern University. So let's begin. So talking about motors, and it seems that nature made motors before humankind, much earlier than humankind found it, and because nature motor is very very tiny in our bodies, in the cells, and they are very important. For instance, that a motor proteins known as ATP synthesis which produce the ATP, and it is, and as we know, ATP is a short-term storage and transfer of energy. So they are often we cannot live without of them, and and about 200 years ago, and humankind made the first electric motor, and that's why we have the electric cars today, and we also can find it in many machines like coffee green automatic coffee grinders, and they help us perform works in our everyday lives. So they are very important, but compared with the natural molecular motor, is still very big. So can we shrink the motor? And this is a question raised by Professor Richard Feynman, and he is a very famous physicist at Caltech. So and the story about him and the smallest motor is begin in December 1959, and at that after a dinner talk to the West Coast section of the American Physical Society, he gave his famous lecture, and which he titled "There is platinum of long at the bottom." So in his speech, he announced that it is his intention to offer a prize of $1,000 to the first guy who make an operating electric motors, which is only one only 0.4 millimeters cube. So which is like 16/4 inch. And after the talk, a physicist who won a Nobel Prize in 1916, and Don Glaser, and he told Feynman, "You should have made it smaller." But the thing is that but Feynman seems very confident. However, after 1 year, a previous graduate student, Bill McLellan from Caltech, he did it, and as we can see from the slide, he made a very tiny motors, and in the bottom picture, and Feynman will check the McLellan's motors under the microscope, and Bill won the $1,000, but Feynman was a little disappointed, but not because he lost the $1,000. Actually, is because the motor was made by wasn't made by new method. So, and Feynman thought maybe we should use new technology to make it. So even though the motor itself didn't produce what Feynman wanted, but the result get everybody interested in this field, and the motor was indeed the smallest electric motor at that time in 1960. But compared with the natural mercury motor, it was still too big. So can electric motor be smaller than that? Yeah, as the science and technology developed during the past 50 years. So now we have nanotechnology. And the next slide is very good examples. So it's DNA microscopic electric motor. So last year, a research team led by Diaz from Technical University of Munich, he produced the first molecular electric motors, actually electric motor using DNA origami method, which is made of DNA self assemblies, and can convert the electric energy into kinetic energy. And this motor can be divided to 3 parts, and one is base, and the other is a platform, and also a rotor. So the platform is very important. As we can see, it is between the base and the rotor arm, and it contains obstacles that can influence the movement of the rotor arm. If we look at more clearly to the platform, we may see some similarity between it and the ratchet gears in our daily life. So, and that's why the motors can have the unidirectional motion. And also, if we look at the rotor arm, it's around 500 nanometer, which is actually 1,000 times smaller than McLellan's electric motor. So it's a very big breakthrough. And but the question is still there? Can we make a smaller one? And the answer is yes. And actually, somebody already did it in 2011, and it's Professor Sachs group at the Tufts University in Boston area, and he made his group and some other co-workers made the world's smallest electric motor. It's a single molecule motor, only 1 nanometer wide, and as we can see from the right figures, it only contains 5 carbon atoms plus 1 yellow sulfur atom, and several hydrogen atoms. So, but the operation of these single molecule motors will require STM, and which you can find in the figure, in the photo of Professor Sachs, the red square, and behind the window it is the STM, and there's another maybe student who is working on it. So we need to use the STM tips to give the motor electrons so that it can rotate on the copper surface. But it is not easy to get the STM, and if we want to use the STM with ultra high vacuum system, it is not cheap. So can we do it in another way? So synthetic chemists have the own way to solve this problem. If we look at the next slide, artificial molecular motors. So here are 2 remarkable examples, and the top one is from Professor Ben Franga's group, and Ben is a Dutch organic chemist. He was awarded the 2016 Nobel Prize in Chemistry, together with my boss, Sir Fraser Stoddart, and Jean-Pierre Sauvage, for the design and synthesis molecular machine. And his motor is a light-driven rotary motors based on overcrowded alkenes. So a full 360 rotation process of his motor included 2 photochemical chain synthesis isomerization, which are each followed by a thermal irreversible helix inversion. And the bottom one is from David Lay's group at Manchester University in UK, and Professor David is one-time student of my boss, so we can say we are in the same group. We are from the same group. So he's very famous scientist in the field, and he made a lot of beautiful work of molecular machine. So in the figure, the motor developed by his group is based on a 3 catenane. So a 3 catenane is made of 2 small rings interlock with a larger ring, and the 2 rings can rotate independently and unidirectionally around the larger ring. But in his case, he's using chemical fields, just like biological molecular motors employ. And but if you use chemical fields, it will generate waste. So can we make electric motor, since we now have light driven chemical? Can we make an electric one? So that's why we doing the research I'm going to talk about. So, but first, before that, I would like to introduce mechanical bonds. So the next slide is mechanical bonds, and what is mechanical bond? We know chemical bonds. There are 3 kinds of chemical bonds: ionic, and covalent and metallics. And the common issue is, of them is sharing electrons. And for mechanical bond, I would say the 10 of mechanical bond was used not in molecular, not in chemistry, but in our daily life. So but we can find the mechanical bonds in many of things, like toys, as we can see here from the right figures. So the toys, most of child, including my son, have plan like very often, and it contains some rings and some blocks, but interlocked with a string or other things. But if we shrink the toys into molecular size, so then we will have the mechanical bonds between molecules. And there are two kinds of molecules named catenane and rotexins. So catenane is based on two interlocked rings, and rotexin is based on a ring molecule thread over axles with two bulky groups, the green one, and so that the ring cannot thread outside. So it's formed a mechanical bond. So unless we break a covalent bond, either of the ring or the axles, then only in that way the ring can come out. So we can separate the component inside the rotexin or catenane. So talking about the mechanical bond, I would say my boss, Sir Fraser Stoddart, play a key role in the creation of such kinds of bonds. And the next slide, mechanically interlocked molecules. And so if we look at the cover art on the slide, on the right part of slide, of unwanted chemie in 1989, this is a breakthrough for the creation of the 2-catenane. So the 2-catenane is the yield of the 2-catenane is 70%. So it's the formation of the catenane is used a method called donor acceptor templation. So before that, and like 6 years ago, Professor Savage used a metal ion templation, achieved the high yield formation of the catenane compound, but except that examples, so that the yield to form the mechanical bond is very low, like 0.001%, and we can only see the formation of the product in mass spectra. So, and because of that, and after that, many people were joined this field to make the mechanical interlocked molecule, and then in the group, after 2 years, and Fraser made the first molecular shuttles. So it is the ring molecules which can the blue ring can switch in between the two binding sites, is the two benzene sites on the linear axles. So it can switch very fast because the ring has the same binding affinities on the two benzene rings, so it shuttles very fast. So this is the beginning of the field of Merkle machine. So, and then after that, and it's about 30 years, more than 30 years, and now we can see we produced a complex and more complex Merkle machines like motors with more functions, but before that we need thanks the pioneers for the work on the mechanical bond. So, and then now we come to the radical pairing interaction, which is very essential to synthesize the electrical Merkle motors we made. So talking about radical pairing interaction, it's just like electrostatic force. So the like charge, we know the like charge will repel each other, and opposite charge will attract each other, and it's indeed the same as the radical divergence. So the 2 plus blue blocks is divergent. So the divergent is organic reductive molecules which can undergo to 1 electron reduction in steps. So it's bipyridine, and if we reduced it to its radical state, give 1 electron to it, and if we also have rings which on its left, it's in the reason why it's in blue color, because once we reduce the divergent to its radical state, the solution color is blue. So, but if we mix both the ring and the dimethyl divergent together in reducing condition, the magic thing is that the dimethyl divergent can go inside the ring to form a complex molecule. So, and if we oxidize the complex, and then they will dissociate because of the Coulombic repulsion. And so then we can use these properties to design an energy ratchet. And then we now come to the next slide. So the energy ratchet, to design the energy ratchet, we need to have some unique units on the linear we can say it's dumbbell like axle. So we know ratchet gear in our day life. The ratchet, if we have a design of ratchet, it will allow only one direction motion. And if we made one charged here on the left figure, if we made one charged group, which we use pyridinium on the left, and the other one, the neutral green unit, which provide a steric barrier to prevent the rings come from the right side. So now we can look at the motion. Firstly, we reduce it, and because the ring changed from 4 positive charge and to 2 positive charge, So it now can thread past the pyridinium, the only one charged blue unit on the left, and this reflect on the energy surface that the barrier was decreased, and so the ring can can pass the barrier and go to bind the center Wilgen binding site, and now the center Wilgen become an energy well to trap it. And after that, if we oxidize it, the repulsion, the Coulombic repulsion will come back, and the barrier from the left will increase. So this time the ring can only have one way to go, is to pass over the green neutral steric barrier and go to the right side. So here I would say it's just surfing on the energy surface, just like surfing on the sea. So and the difference is that we use energy from fluctuation to regulate the motion. So, and after design the energy ratchet, so we build the artificial molecular pumps in our group, and it was done by two previous group members, Chu Yangchen, and he now is a professor in Sichuan University in China, and he produced the first generation molecular pump based on the ratchet energy ratchet I said. And then Christian Pizzato, he is now assistant professor of University of Padova in Italy. He made the second generation. It's just like iPhone 8 to iPhone 10, iPhone X. So, and the molecular pump is as shown in the middle figure, and it's a linear. It's a rotaxane based pump. Has a linear axles, and can pump the rings from the solution and into the collecting chain on the linear axles, but with stoppers to check the rings on the collecting chain. It can continuously work through multiple redox cycles. So every redox cycle can pump one rings onto the collector chain by utilizing the energy ratchet mechanism. So as we can see, the rings, if we reduce the rings, the ring can go into the middle between the blue and green component, and then oxidize the ring will choose to follow the green arrows, pass over the green unit and to the gray cracking chain. And we published a lot of work on this field, but we haven't before based on this previous result. Christian has a simple idea. Just if we can connect the head and the tails of the pump, then we can make the two catenane motors. But it's not easy work. So the synthesis of the two catenane motor hasn't been done yet, and because of some problems. And I think one of the biggest problems is that we cannot find a way to prove whether it's achieved the unidirectional notion or not, because after after every redox cycles, two catenane will always become returning its original state. So then I came out the idea to make a 3 catenane. Now we came to the next slide, molecular design and the 6 structures. Here we can treat the design of the 3 catenane like we use Lego to build a structure like that. So the Lego unit we need to use is a Columbia barrier, and it's a pyridinium, and we need to Violin recognition site, which we can use repulsion and attraction, and we also need the green unit, the steric barrier, functional as a one-way gate, a ratchet unit, so that we can have the energy ratchet, and to form the ring, and we will use click reactions to generate a triazo group in pink color, and this is the final step. And we have linkers between the 2 Violin recognition sites named BPM, biphenyl methylene linkers, which is a relative rigid linkage, and the rigid part of the unit is that it has only 1 nanometer wide, and because of the length, we can have some interactions between the rings once the rings on the recognition site, so that we can do the ring closing reaction easily, and that's why we can make it. And the structure is just like what the models on the left. It's not a crystal structure, it's a computational structure. So we see 2 rings on like 3 and 9 clocks position of the larger ring interact with the larger ring. So how it works? So here is the mechanism on the how it works slide, but before talking about it, we need name the left ring A and the right ring B, AB. We distinguish them so that we can see the position after 1 redox cycle. So first step is to reduce the 3 catenane. We give the molecule 6 electrons, and now all the Violin units will become to one radical and 1 charge state, and the color will show here is purple, because the solution color is purple, and then the ring will start to move. So because the green unit is functioned as a steric ratchet unit, so the ring will be prevented to go back to the bottom, and the only way it can go to pass over the 1 charged pyridinium unit, the blue one, and to go to the top, the 12 o'clock, and then ring B will go to the 6 o'clock, the 6 position, and after that we can oxidize the molecules, and by taking away the 6 electrons, and because of the repulsions between the component, so the rings will starting to move, and also because the one charged pyridinium on the left side of ring A, and ring A will choose to move to the right side because right side had no repulsions. And then this will influence the motion of the ring B. Because on ring B, both left and the right has no repulsions, but ring A will choose to move to the right. And the interaction, the electrostatic interaction between ring A and ring B will force ring B to move to the left to pass over the green steric barrier. And now ring A and ring B is on the 6 and on the 3 and 9 position. As we can see, after one redox cycle, ring A and ring B exchange the position. And this is how the motor works during one redox cycle. And another redox cycle will bring the two rings go back to its original state. So, but why we need two rings in the design, in this design? And if we look at the two, only one small ring on the larger rings is two catenanes. We calculate the energy landscape of this molecule, of these two catenane, as shown in on the right part, like a roller coaster style. And in the oxidized state, the ring will trap between the two valence units as the biphenyl, the black component on the larger rings, functional as the energy well. And if we reduce it and then go back, the ring will always trap it. So, which means it should have no chance to pass over both the green unit or the blue unit. So that's why we need a second ring. So the two catenane is only a molecule switch from here to there. So to prove I am a synthetic chemist, so I show a slide of the synthesis of the three catenane, and is the final step of the synthesis. So we mix the ring and the linear axles under the reducing conditions in the acetonitrile solution. So the ring two rings will bind on the linear axles because of the bipyridine radical recognition site, and then we add some Cooper 1 catalysis to do the click reaction, and then the click reaction will happen, so to close the ring, and now we can oxidize it to get the final product, and the yield is good, and it's around 40%. So it's good to have that kind of yield to have a 3 catenane. It's not easy to make mechanical bond. So, and now we after get the product, we can oxidize it. We can characterize it using some technique like proton MR. So we test it according to the spectrum we got. We can confirm the position of the two rings. So one is on the 9 o'clock, and the other one is on the 3 o'clock position. So and for the reduced state, we can, because it's a paramagnetic, we cannot get the MR but we fortunately get the crystal structures. Crystal, I think every chemist like crystals, so it's the most straightforward to see the molecule, the structure of the molecule. Now we get the crystal structure. We can confirm the binding of the rings on the two Wilgen binding site. Here is the purple purple part, and we can see, and we also can see the whole structure of the larger rings, just as we made. So the size of the whole molecule is around 2 nanometers length and 1.5 nanometer wide, and the depth is maybe 1 nanometer. So, and it's very nice to have the crystal structure. And after that, we need to demonstrate we can use electricity to operate it, and then we do the redox cycles in the electrochemical cell. So in the oxidized state, the color of the solution is colorless. But if we set the reduction potential to negative 0.5 volt, and then the solution will be reduced to purple color, which is characteristic of the trace radical complex, and demonstrate the rings was moved to the Wilgen recognition site, and then we can reset the potential to positive 0.7, and which can oxidize the radical state and back to the fully charged state, oxidized state, and the solution will come back to colorless. So, and until now, we just demonstrate the molecule can be switched between the oxidized and this reduced state. We need to find some evidence for the unidirectional motion. So how can we make it? How can we demonstrate it? And here is our solution. We synthesized the deuterium labeled small rings. So we incorporate it with another ring to form a delabeled 3-catenane. So that now we have delabeled small rings on the 9 o'clock position and unlabeled rings on the 3 o'clock position. So as I showed in the mechanism, after one redox cycle, the two rings will have position switch. So showing the MR spectrum will be the signal switch. So according to the signals, and we indeed see the signals of related to the rings switched. According to the integrals of the signals, we can calculate the efficiency to be 85%, and which means in the solution, 85% of the 3-catenane molecules has finished unidirectional motions, but the left 50% will go what's going back to its original state. So it's not doing a reverse cycle like that, but just going back to its original state. So this is one evidence. Another evidence is metal step state we observed during the reaction. So after we oxidize the reduced state, we immediately took the protein MR, and as shown in the red color in the spectrum, and it is much complexer than its original spectrum, and many other peaks were shown. And after analyzing it, we find out it's a meta-step state, and one of the position of the ring can be confirmed from the spectrum, and that is one of the ring was encircled on the top part of the biphenyl methane, the black unit, and the other one was just was encircled the green unit, was going to pass it over it, but not because of the barrier. So this is another evidence for the rings for the rings unidirectional motion, and this is pretty all about the research. And now I'm going. The next slide is some story behind this research, and it is about mechanical quantum mechanical calculation. So because our molecule has hundreds of atoms and has two rings, and the two rings will have interactions not only with the larger ring, but also the two ring the two ring will have interaction between each other. So we seek the help with calculation from Bill Goddard from Caltech at the beginning of 2021, and he replied us and sent us a schedule for the Zoom meetings. The first round, I thought, oh, we have 4 months Zoom meetings on every Sunday week, every week Sundays. Do we need so many meetings? But actually, after the first round, we have second round and third round. So the total numbers of the Zoom meeting we have to discuss the calculation is 59, and it took us more than 1 year. And because of we are from Bill is from Caltech, and Dean, another professor from he's a physicist. He's a molecular machine theorist. So he's a professor at Maine University, and Wei Guang, a postdoc from a former postdoc from Bill's group, and we all from different areas. So, but we spend like 1 hour on every Sunday week to discuss these calculations. So it's just like a routine things for 1 year. It was a lot of fun. And the next slide is the timeline for the research. So at the beginning June 2018, I have the idea to synthesize the 3 catenanes. I have the design, but after 3 months, I get it. It took me 3 months to get it, to make it, to synthesize it. So at that time, I thought I will finish the project very soon. So but it's eventually take me more than 4 years. So after we get it, we need to think about how to prove the unidirectional motions. Until 2019, I get the idea to delabel one of the blue box, one of the small rings. And then, luckily, in April 2019, I get the crystal structures of the 3-catenane in radical state. And then it's another 6 months. We observe the metastability and analyze it, and then I produce the first draft, but unfortunately, the COVID happened. So, and our lab was shut down, and the university was shut down for like more than half a year, and then back to 2021, and we returned to the lab and modify. But during the time, we modified the manuscript for several times, and my boss thought we might need to do some calculations to get more insight of the mechanism. So we seek help from Bill Goddard at Caltech, and it took, as I talked before, we took more than 1 year to finish the calculation, and then we finished it. So now we can see after the calculation we combine the calculation part and the experiment part, and we revise the manuscript and decide to submit to science firstly, but unfortunately it seems like the editor didn't like our research, and he didn't send it out for reviewing. And then we submit to Nature, and finally accepted, and we were very happy to see the result. So now we can compare the because I told that Professor Lei also made a 3-catenane motor, a chemically driven. So 5 years ago. So what's the difference? And I think the major difference that because we use electricity as a power, so we are the motor we made is an electric motor, which means no waste will be produced. And another one is that in our case, we don't need to break any covalent bond, so it means it's a simple design, and the efficiency, the unidirectionality is similar, around 80%, but the time scale in our case is much faster. So we can finish it 180-degree rotation within several minutes if we use electricity. But if we use chemical as a fuel, it can be finished in few seconds. So we can call our motor is a hybrid motor powered by electricity or chemicals. So the next plan of our research is put the motor on the surface, because if we leave it in the solution, so no useful work was being done. But if we are able to attach these motors on the surface, maybe some useful work will be done in such kind of way. So here is two kind of way we can make a 2-catenane. and the 3 catenane type, and how to attach it. Then on the surface is that we can function one of the small rings, and so that like we attach a chain, a linear chain which has sulfur atoms on it, and so the sulfur atoms can anchor on the metal surface like copper or gold, so that the catenanes can many of the catenanes can attach on an electrode. So if we have some uniform, we can attach the catenanes in a uniform way. Then maybe we can use it to clean the surface of the electrode, or move some small molecules on the surface. So it's just a future plan. And talking about the near future, if we look at the synthetic molecule motor, I would say are still much less capable than either biological or macroscopic counterpart. But if we look at the first electric motor made by Noise Jedlicks in 1928, 2,000 years ago, 200 years ago, and I don't know at that time what people think it can do anything, but now we have Tesla electric car, and which is made based on this the same principle of electric motors. So have a high speed, and we can drive. It can be used to move us to anywhere too. But so now we have the I would say electric motors, and after 50 years or 100 years or 200 years, what would happen? I don't know. Maybe we may we will have molecular robot. But to realize it, I can say it definitely need other scientists from like physicists or engineer or materials. All of us came together and work together to and collaborate together. Only in this way can we can see the molecular robot in the future. So yeah, this is the final slide is many thanks to my mentor and to collaborator, and first Professor Stoddart and Professor Goddard and Professor Astumian for the great support in this project, and also my collaborators, and many of them during the past 5 years has become professors in academia, and some of them are still in the lab. And many thanks to all of you, to the audience, and any questions are warmly welcome. So.
Well, thank you so much, Long. This was such a beautiful story with like success but also like pain and struggle and success again. And this was so much hard work. Thank you for sharing also the path that the timeline and the path and how much work it was and how many meetings and so on this took, because that gives us really a peek behind the curtain. So thank you for this wonderful talk. You brought us the story on many different levels and aspects of this work, the technical, but also the human part and the hard work part. So this was really wonderful. Thank you so much. And my question, and then I'll give the mic to others here on the stage that for sure have questions. I wanted to ask, you mentioned a little bit the upsides of your molecular motor. Does also I read that also the conditions are easier to have this functioning, right? Before the temperature needed to be, or did it need to be even in a vacuum? What are the conditions in that these motors can function?
Oh, just the room temperature, and the only thing is that we need put it in inert atmosphere, which which doesn't contain oxygens, because oxygens will oxidize the reduced state. So if we want to just use electricity to reduce and oxidize it, and then we need to preclude the oxygen. So that's it.
Yeah, that's a huge upside also, right, to the previous the previous designs, that you can just have it in room temperature.
Yeah, yeah. So for
Yeah.
the single molecules motors, I think the orders there that they need to measure the rotations at a very low temperature, because like 5K, because at room temperature maybe like they said in 100K, so the rotation for the single molecule is around 1 million times per second. So we can imagine at room temperature maybe hundreds million per second. So
Yeah, and to produce a lot of these motors, let's say, for, I don't know, microchip company to keep their components clean or something, like how many of these motors could be produced, and would it be very expensive, or
oh, so for this one, compare with the three catenines developed by David Lay's group, Professor Lay's group. So the molecule needs 25 step synthesis. So it's not easy. But for our one, only 4 steps based on some previous precursors are needed. So we can make it in right now. I would say in several milligrams as no problem, or 100 milligram or gram scales if we have enough materials. So it's not too difficult to make it.
Wow, that's so impressive. That's wonderful. Thank you. And now I'll pass along to, I don't know, Victoria, if you had more questions. If not, Dr. Shah, and then we can just go in order. Thank you.
Let's pass to Dr. Shah. Thank you.
Yeah, thank you so much, Lang, for your wonderful talk. So, two aspects just came to my mind that I had a question about it. One of them is the combination of these molecular motors with the synthetic polymers and how it might be the result. For example, if we want to consider something like the for example, electrolyte membranes, how they are functioning properly and what might be the result, for example, in a case of the stability or specific selectivity or multi-responsiveness. Do you have any further information, or do you think how it might be working that way?
So for the if we talking about the motors we made, if we touch it on membrane or some other polymers, the first question or the first issue is that how can we let the motors get the electron or lose an electron easily? So I prefer to attach the three catenane, the motors on an electrode is because once we attach it on the electrode surface, it can easily be reduced or oxidized much faster than the molecules in solution. But it doesn't mean when we put them in the membrane or in other polymers cannot be operate because we can use chemicals to reduce it to oxidize it. So, but I don't know how can we utilize the unidirection if we put them in the membrane. Maybe the rotation of the motor will destroy the membrane, and in some literatures, someone actually use motor molecules to do such kinds of things to kill the cell, and this is one of the applications I would say. But other than this, I don't know.
So, for example, you can imagine that they can help with the converting the chemical energy, for example, or other kind of fuels into electricity.
Yeah,
Okay, and actually, they can do the proton exchange in the same time.
yeah, we can use chemical to reduce it and oxide it, but it cannot generate electricity.
I see. So if in some cases it can produce the electricity in the case of the, for example, for using the small battery power devices or those kind of things.
Uh,
In comparison, using that, you can compare it, for example, with some of the cases that we have, for example, cathode materials that they are using in a lithium
mm,
ion batteries.
mm. You mean
Yes, with considering this hypothesis that they are able to, I mean, convert the electricity. Do you have any idea about the use of that in energy storage or
oh,
kind of a small
and
battery power?
storage? Oh,
Yes,
talking about that. It So hydrogen units has been used in energy storage in the application of energy storage. Someone use it as because it can accept electrons, and it also can it is redox active. So it means it can accept electrons or lose them. This is a way, one of the way to achieve this energy storage. But the thing that why we need to use motor molecules to doing this job, to do this job, and and I think maybe we don't need a motor molecule, just some Wilgen polymers or or in other ways. Uh, maybe or maybe you are right. Maybe we can uh, utilize the unidirectional motion, but I don't have a idea on that. But you are right. It, it, it can be used in energy storage area. So
so thank you so much for explanation. I'm passing the mic to the next person.
thank you.
Thank you, Dr. Long. This is a really, Dr. Zhang, rather, this is a very interesting discussion Definitely learned a lot. I was curious, how long does it take to manufacture this type of motor?
Hello, I didn't hear your last part. So what's your question?
How long does it take to manufacture this type of motor?
Oh, manufacture this type of motor. You mean, do you mean synthesize this type of motor, or?
Yeah, how many days, hours, weeks?
Oh,
What's the time frame?
so once we overcome the roadblocks on the synthesis, we can do it within 1 week. But if we have all the materials in hand for the reaction of the final step, it takes 2 or 3 days.
Okay, wow. So that's a pretty short time frame. Do you think that's as good as it's going to get, or do you see room for improvement on the time frame?
Yeah, I think that there's still pretty room to improve it, and it depends on the synthetic method. And maybe in the future some green synthetic method will also be developed, like solid synthesis or electron synthesis, mm, or using electricity, just use electricity to generate uh, the the catalyst of the click reaction in shoot, so that we can do the reaction in the electrochemical cell. Maybe. Yeah, we have a lot to improve that in the future.
Certainly looking forward to that. And last question, um, what's the most practical application for this type of technology, would you think? Like, if it were to be commercially available tomorrow, what do you think would be a typical use for it?
A typical use of that, to be honest, I would say uh, no no application at present. It's just like a toy for a child. Uh, it's a toy for like synthetic chemist like me. So I think that the most interesting or the most important thing that it can keep us imagine the future. So what would happen? So it's not about the application at this time, and it's about what can we do, and how can we do. And this is my my answer to your question.
I appreciate it. Yeah, I understand. Hopefully, there will be, at some point, there will be some life-saving applications of this technology. So looking forward to that and passing it to Eli.
Yeah.
Hi, thanks, Dennis. A couple of quick comments and then some not so quick comments. The molecular machine that you drew, with especially like nanorobots for medical applications. I honestly don't think it's more than 2 decades away. Hopefully less than 1 decade away. There are a lot of shortcuts. Anyway, I really like Dr. Shah's question about the membrane, and I would encourage you to think about whether electron transfer through a conjugated chain like the chain of beta carotene might get electrons, to the middle of a membrane where perhaps the smaller um, the smaller macrocycles are kind of buried because they have long alkyl side chains, right, to make them hydrophobic. And
Yeah.
then you could have the larger catenane going through two of those, right, so that
Yeah.
it's like a conveyor on the membrane. And if the membrane has some conjugated molecules like beta carotene, that my guess is, and it is only a semi-educated guess, but my guess is that could do it, especially if you do something with the head groups to make them convenient in terms of the redox chemistry.
Mm, a very good point. Yes.
So the other quick point is that one of the easier things in your immobilization to the electrode that would have to be different than what you drew is the macrocycle that's anchored would need two bonds to the surface to keep it from spinning around, or you'd lose orientation.
Mm-hmm.
Right. So but I think that would be easily accomplished by having substituents on the methylene bridges between the aromatic rings. Just like two of those would probably, two thiols, two thiol alkyl thiol chains hanging off the side would probably do it. So I did think more about how to template the desired topology from when we last spoke. And so the question, and if the answer is yes, that would make it easier, would be, do you suppose that the one of the methyls of the isopropyl group and one of the methyls on the dimethyl pyridinium group
Mm-hmm.
could be substituted with, say, hydroxyls?
Hydroxyls. I don't know. Maybe it will change the steric barriers. So maybe it will. It's uh hydroxyls maybe too big.
They're not much bigger than methyl groups.
Maybe it could. Yeah, if they have similar size, maybe it could. Maybe
So
the
so if that's the case, there's probably a large enough range of choices in terms of orthogonal conjugate chemistry, like selected from bioconjugate chemistry, for example, um, to be able to to make a chain out of the larger macrocycles and then use deep protection chemistry to free them. Do you follow?
you mean made a function of the larger chains with a long another long chain?
Well, okay, so remember, we want all of the if you're trying to do what you have on that slide, we want all of the larger macrocycles to be oriented in one direction,
Yes.
right?
Yeah.
And so one way of doing that is to make a head to tail chain out of them in some
Yeah,
way.
but the head and tail chain will be on the small rings, not on the larger rings.
You could, well, what I'm describing, you could do it on the larger rings.
On the larger rings, it will block the motions of the.
Well, okay, but see, this is the thing. You use the hydroxyls to make the chain, right?
Mhm.
But you do it with something that you can cleave
Oh yeah.
through like standard deep protection chemistry,
Mm-hmm.
right? So, which can be high yielding.
Mm-hmm.
And so this is how you can get all of the large macrocycles pointing in the same direction. There's a little bit more to this but it's things that I've done when I was doing scanning probe microscopy of molecules on surfaces. So I think this is a very tractable problem.
Oh yeah, yeah. Just might be a solution for how to orientate this molecule in one way. But the problem will back to how to synthesize it, how to make it.
Yeah, and that's why I asked the question about the hydroxyl substitution. You know, I don't have so much of a feel for the chemistry
Mhm,
that you used at every step, and whether I mean, you could probably have have protected hydroxyls
mhm,
in there. But you know, that always is one of the things where you have to go into all of the details to make sure that nothing interferes with any other reaction along the way.
mm.
Um, but I mean, the idea is to turn this into a problem like peptide synthesis or oligonucleotide synthesis.
Yeah.
So
Thank you very much.
anyway,
Yeah.
glad to discuss it further, whatever you feel like it.
Yeah.
Yeah, thank you so much for those questions. Kush and John, did you have questions?
Well,
Uh, Hello everyone, hello respected sir and ma'am, dear brothers and sister. I'm from India, Kush Sharma. So sir, hello long sir.
Hi.
So yeah, hi. So sir, my question is that so it is developed this motor. So can you tell me about some technical specification regarding this? And apart from this, I'm curious about this motor. So how can you like construct this motor so that it is like efficient and stable in terms of losses and other environmental criterias?
Do you mean the application?
Sorry.
So do you mean the application of the motors or
No, no, no. I'm saying that can you reveal or can you look out like can you give some details about the technical specification about this motor or what are the environmental aspects about this?
environmental aspect?
Yes.
Uh, how I don't know how to start. So do you mean the operation environmental or its its influence on the environment?
I'm looking as like if I'm using any electrical motor, so we usually looks like a losses in terms of heat, vibration, friction, mechanical losses like that. So in this motor, which kind of losses are and how you are like rectifying those losses?
Mm. What do you mean losses? Sorry.
Yes,
May I help here for a moment?
Sure.
Uh,
Yes.
Kush, yes, sorry, Dr. Long. Kush, thank you so much for joining us here on stage in Science Society. I'm curious if you have read the paper, and perhaps that would answer some of your questions. If you go and take a read through the paper, and if you still have questions afterward, then you can feel free to contact us. If you can really streamline your questions after reading the paper and make them very specific, because that's a very broad question, and Dr. Long has just given us a very at-length read through and description of that. So I'm asking that you in turn spend a little time in the paper and then try to fine tune a question for us. So thank you so much. And John, do you have a question?
Yes, actually, I have first, let's see. Yeah, this is a very wonderful molecular machine. and I can think about it, see like a couple, see like a source for the electrons. Well, in life, well, we also know that mitochondria has a huge, see like a mitochondria and chloroplast. Those are the two, see like a major electron producing mechanism chains. So if you could somehow link those your machine to those chains, then that would be I think that would be you should achieve a lot of stuff. You have an endless energy source. Second, I want to see that is because of the two rings, they move. Uh, they move against each other. So they must generate some kind of like a water current or some kind of disturbance within the environment. So if we can use those disturbance or something force generated, then we can make things move. At
Yeah.
least make this machine itself move. So, and I think that then this might be a very prototype of like a robot, and then because it can move around.
Hmm.
That's just some of my thoughts. Thank you.
Thank you. Thank you very much for your valuable comments and suggestions. Yes, it is. And because it's redox driven molecular motor, so that means any redox chemistries or redox reactions can have the potential to power the motion of our motors. And you are right. If we can somehow make the unidirectional motion of make use of the unidirectional motion, maybe we can utilize it and make the whole molecules move in a surface or in some environment in unidirectionality. So thank you.
Actually, there are some like iron channels in membrane, and so those iron channels, of course, their mechanism is a little bit different from the your motor, but still it uses those iron concentration difference
Mm-hmm.
and then to open and close the channel.
Mm-hmm.
Oh, I'm sorry, no, backwards. It's they take some kind of electronic signals
Mm-hmm.
from neuron or from somewhere and then to open and close
Yeah.
the channel. Yeah, so those to me those might be another way of thinking about this electronic motors.
Yeah.
Okay, thank you.
Thank you.
Well, thank you so much. We are spending now almost like over an hour and a half, so I wanted to check in with you long. I
Mm-hmm.
guess you had a long time that you had to speak, and it was such a great presentation. I don't want to stretch your patience too long and take too much of your time. And I think everyone got the chance to ask questions, so thank you so much for this wonderful presentation. Oh, Eli, do you want to go ahead?
Yeah, so a couple of quick things occurred to me. If the hydroxyl turn out to be real problems, at least the one that would be substituting into the isopropyl, that could be converted back to a methyl group with triflate or tosyl chloride and a nucleophile that arises from a methane halide, right? Or a Grignard methyl grignard. That would be the easier one. The on the pyridinium, you could. I don't have a feel for how good the yield would be, but there are some decent yielding Suzuki couplings that use triflates. So there it would be converting the hydroxyl to a triflate and then trying to do. Actually, it's not a Suzuki coupling when you put an alkyl on an aryl halide with a palladium catalyst. I think it's a still coupling, but you know the chemistry that I'm talking about, right?
Yeah. So the question is that how much time I have in the school and do the
Ah,
experiment. I think this is a big question or big issue.
well, you know, if anybody wants to pursue it, there are pathways.
Yes, yes. Anybody want to pursue it? Yes.
Well, thank you for those last comments, and I think it's really interesting when people come together from different backgrounds and share new ideas, and maybe somebody will take the idea and study it further. That would be great.
Yes.
Well, again, thank you so much for your time and for this wonderful presentation and for answering a lot of our questions. It was really an honor having you here, and we wish you all the best for the future, a lot of grants, and I'll hope we hear you someday again, and we will for sure follow your work. It's so interesting, so we will cheer you on for the future. Thank you, Long.
Thank you very much. I enjoyed the conversation tonight, and yeah, hope I can have another chance in the future to talking with you again. And thank you very much.
Yeah, thank you. And thanks everyone for coming and asking questions. It's really a much more rich conversation when many people contribute to the discussion. So thank you for that. And if you like discussions like this, follow the club. The next talk will be on Tuesday from the Allen Institute. Um, doc, Dr. Rafalski. She did a new math framework to study cell organization and came and discovered new novel insights into how cells are organized. And tomorrow we will have again a room to make awareness for getting donations to the relief of the earthquake um, victims that are currently still struggling and don't have a home. And we will have again wonderful music from our from Nicolo, a DJ that is relatively, famous here on Clubhouse that Victoria invited again. And yeah, maybe you come and join to support that room too. It will be a mixture of some information about the current state from friends in Turkey, and then also some music just to listen to. So thank you so much, everyone, and enjoy your weekend.
I've posted the room link in the chat for tomorrow in case anybody would like to join us.
Perfect, and thank you, Victoria, for organizing this. It's a wonderful initiative. So thanks, everyone. Happy weekend, and I hope I hear you all back soon. Thank you. I'll
Good night.
close. Good night. Thank you. Close the
Bye.
room in 3, 2, 1. Bye, everyone.